All right, in this chapter, we're going to talk about linear momentum. Okay, so let me define the vector p is equal to a mass times a velocity, right? So this thing is the momentum. So we can take a derivative in time, get dp dt is equal to d by dt of mv, which is m, dv dt, which is mass times acceleration. Now, by definition, this is just the net force. And so we have that dp dt is equal to F net. Okay? So let's consider two or more objects. M1 is here, M2 is there. This is R1 vector, R2 vector, say. And we define M1 R1 vector plus M2 R2 vector divided by M1 plus M2 as RCM. This is the center of mass. Right? Or at least the position of the center of mass. So, that being the case, if I also define the total mass, well, it's not defined, it's actually true, it's M1 plus M2. Then what I have is that the total mass times RCM, which just is the total mass on the bottom, that's just M1 R1 vector plus M2 R2 vector. Okay, now we're going to take a time derivative of this entire thing. D by dt, d by dt, right? And if we do that, right, we can get something that looks like this. This is m total, the RCM vector dt is equal to m, d by dt of R1 is v1 vector plus m2 v2 vector, right? So this right here, you can think of that as total mass times VCM, right? And this thing now is the total momentum, or the system momentum. I'll call it total momentum for now, all right? Okay, so now let's take another derivative. All right, so now this is dp total dt is equal to d by dt of m1 v1 plus m2 dv2 dt, right? That's just ma1 plus m1a1, m2a2, which is just the net force on one plus the net force on the other, right? Now, if the net forces are due to 1 on 2 and 2 on 1. So there's no external forces here, right? What that means is that F net on 1, that's just basically the force of basically 2 exerts on 1. F net 2 is equal to the force that 1 exerts on 2. All right. Then what we have is by Newton's third law, F of 1 and 2 is equal to minus F of 2 on 1, right? That's just Newton's third law, okay? And so what that implies is that dP total dt, which is F net of 1 plus F net of 2, right? That's just that term right there. That's equal to F of 1 and 2 plus F of 2 on 1. These are equal and opposite in sign because of here. It's equal to 0, okay? And so what that implies at the end of the day is that the total momentum, which is P1 plus P2, is a constant, right? In other words, the total momentum is conserved, right? Okay, so this is called the conservation of linear momentum. Okay. Now, it's cool, right? But it's very useful to basically look at a few examples to learn how to use it. Okay, so let's look at a few examples here. Okay. So the first example is we have a frictionless sled here. Okay, and this is on some surface, say, for instance, and some person is running off, right? And basically jumps off at 3 meters per second. So V is equal to 3, is that right? Yeah, meters per second. All right, to basically start running and just jump off, right? So the question is that what velocity does the sled move at? Okay. All right, so what we can say is that total momentum is conserved. So we have a initial state, which we denote by I, which is when the person on the sled is not moving, and a final state, which is denoted by F, where basically the person has started running to the left. Okay. So the initial state is basically, if we adopt this as our axis, right? P1, let's call this person 1, and this sled 2. Let's call this mass of the person 80 kilograms, and the sled is 100 kilograms, say, for instance. So P1 plus P2 is equal to the mass times the velocity of one initial, the I state, plus the mass of 1, 2, V2 initial, right? That is going to be equal to, well, this is 80 times 0 plus 100 times 0 again, right? So both of them 0. This is equal to 0, okay? Now look at the final state. P1F plus P2F is equal to M1V1F plus M2V2F. So this is going to be equal to 80 kilograms. Now this thing's running backwards. Let's divide this as x-axis as minus 3 kilometers per second, 3 millimeters per second, plus M2 is 100 times VF, which is something I need to find out, okay? So this is basically minus 240 plus 100 VF. And because this stuff is a constant, that means that P1F, P2F is equal to P1I plus P2I. So in fact, these two are equal to each other, which means that this is equal to 0. And so you could do computation here. Vf to f is equal to 2.4 meters per second. Right. So let's try another one. Okay. Same situation again. Right. Now this person this is 100 kilograms again. That's 80 kilograms again. Person stops still and eventually runs off, such that the relative velocity is equal to 3 meters per second, not v2. Okay? So this is relative to the sled, right? Okay, let's do this example now. So the initial state is basically the same as p1i plus p2i. Both velocities were 0, so in fact we know that it has to be 0. Okay? The final state is m1v1f plus m2v2f. That is going to be equal to the initial momentum. That's going to be 0. Right? But the relative velocity is that. So this relative velocity, relative, is equal to v2f minus v1f is 3, right? And so basically I have two equations, two unknowns, right? v1f and v2f, right? So let's basically, let's sort this all out now, okay? So I'm going to set this up. That means that I'm going to try to solve v2f is equal to 3 plus v1f. I'm going to plug in then into here. Let's plug everything in. So this is m1 is 80 v1f plus 100 times 3 plus v1f is equal to 0. So this is going to be 180 v1f plus 300 equals 0. So it's basically implies v1f is equal to minus 300 over 180, which is what? This one is I think it's right. This is minus 1.66 meters per second, right? And then that means that v2f, which is 3 plus v1f, is equal to 3 plus minus 1.66. That's just going to be 1.34 meters per second. So those are the two answers that are possible. All right. Let's do another one. Okay. Let's combine these conversation laws together now. Let me imagine I have a cannon. Balls loaded in there. There's also a platform that's attached to a spring that's attached to a wall, say. Okay? Now, this thing, I'm going to basically say the carrier cannon and everything structure is about 100 kilograms. And say this mass here is equal to 1 kilogram. And it will fire out of it at V of 100 meters per second. All right? So, and the question is that this will fire, and eventually what will happen is that this thing flies away, that cannon is right there, it will recoil, and the spring will be compressed as a result of this, right? And the question is, how far does this compress? Let's say delta x, right? And for initially it was the equilibrium, okay? Equals question mark. All right. Okay, so to do this, there's two steps process, right? We need, this is initial state, I. The final state, F. We need a middle state between the two. So let's basically call a middle state, M. All right? And in the middle state is the moment the cannonball has left the barrel of the cannon. The spring has not been compressed yet. It's just basically, and this moves backwards from velocity, Vm, V2m equals question mark. I don't know what that is, right? So let's call this one 1. I'll call this one, this one to be 2, right? Okay, and this one I know is going to be 100 meters per second, right? Okay, so I got to figure out basically what the velocity is here, and then basically from that figure out this. So from here to here is conservation of momentum. Here to here is conservation of energy, right? So I do two conservation laws at once to do it. So let's just do it. Okay, so the first one is the initial state. That's going to be P1 plus P2. That's all 0. The velocity is nothing's moving yet, right? Okay. The middle state is going to be P, well, we'll write down actually. So M1 V1 middle plus M2 V2 middle is equal to the middle state, P middle, which is equal to the initial state, Pi, which is equal to 0, right? So this is going to be M1 was 1, V1M, this is pointing in the opposite direction, is minus 100. Let's call this X. Plus M2 is 100 kilograms, and this V2M is sometimes 5. Okay? So anyway, this is all equals 0, so it's easy to basically find that V2M is equal to, in fact, 1 meter per second. All right? So that's the middle state that we need. So let's go to the final state. We use conservation of energy. So the middle state, we have E mechanical middle is equal to 1/2. We're just looking at this thing right here. M2 V2M squared plus 1/2 kx squared. And the final state, the mechanical energy, is equal to 1/2 M2 V2 final squared plus 1/2 kx squared. Okay? Now in the final state, this thing is the maximum spring compression, so in fact V2F has to be equal to 0. So that's just 1/2 kx squared. And this state, basically kx, this one, it just left, so in fact kx is 0. So that is 0 there in that case. Right? So we have 1/2 times 100 times 1 squared. That's going to be equal to 1/2 kx squared, which is in fact 1/2 times the spring constant. Let's give this thing a spring constant. K is 100 newtons per meter. So that's 100 delta x squared, which is what I need to find out anyway. All right. And let's go ahead and solve this thing. We basically find that delta x is equal to basically 1. All right. Technically plus or minus 1, but really it's the amount of compression that I require. Right. Okay. So that is part of conservation of linear momentum, right? Okay. Now, I want to talk a little about collisions now. Okay. So, before we discuss collisions, let's just talk a little about kinetic energy, right? So, kinetic energy is a scalar. Right, so it's just a number, like mass. So it can be added together like numbers. Right? So for instance, if I have two masses, this is m1, that's m2. This moves from velocity v1. This moves on velocity v2, then in that case the kinetic energy, the total kinetic energy is the kinetic energy of 1 plus the kinetic energy of 2, right? And so it's going to be equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Okay? All right. Now collisions must conserve momentum. Okay, but not energy. Not energy necessarily. Okay? So basically collisions that conserve energy, these are called elastic collisions. And collisions that don't conserve energy, this is called inelastic. Right? Okay. So let's discuss a little bit about this. Okay. So in fact, so let's talk about collisions in one dimension first. Okay. So if we consider two masses here, m1, collide with some other mass, m2, pushing one v1, v2, say, for instance, right? Then what can happen is that basically the initial momentum, this p1i plus p2i, that's equal to the final momentum, p1 final plus p2 final, right? That's just simply m1 v1i plus m2 v2i is equal to m1 v1 final plus m2 v2 final as well, right? So we're going to a special case of inelastic collision called perfectly inelastic. Elastic. And what this means is that the two masses stick together. And in fact, so what that means is that V1F equals V2F, which is just equal to VF, right? Okay, that's the extra condition there. So what we have is that basically we have M1 V1I plus M2 V2I. That's going to be equal to M1 V1 final plus M2 V2 final. That's just the expression of conservation energy. It's conservation momentum. And V1F and V2 are the same. So in fact, this just becomes M1 plus M2 VF. Right? Okay, so let's try an example of this. Let me imagine that I have a 10 kilogram mass, and here is a 20 kilogram mass. This is number one, number two. This is moving with some initial velocity v1i is equal to 5 meters per second. This one is basically v2i equals 0. Alright, so they collide and they form a single block that's moving with some direction, with some velocity vf. I gotta find that, right? This is 1 and 2, right? Okay, so what that implies is that m1 v1 initial plus m2 v2 initial, that's just 10 times 5 plus 20 times 0 is equal to 50, right? Okay. Now this must be equal to the final state, which is basically going to be here, m1 plus m2 vf. So this is 30, so 10 plus 20 vf. And so you get Vf is equal to 5 over 3, which is about 1.667 meters per second. Okay. So let's see what happened to energy. Okay, let's go work this out. The kinetic energy of the total system is equal to KE1 initial, let's say initial, plus KE2 initial. So that's just 1/2 m1v1I squared plus 1/2 m2v2I squared. This was 0, so that's 0 naturally. This was 5, so it's basically 1/2 times 10 times 5 squared, right? So this is basically 5 times 5 cubed. This is 125 joules, right? Now, well, the final state, KE total final, is equal to KE1 final plus KE2 final. Well, let's just work this. This turns out to be the same mass, so it's going to be 1/2 m1 plus m2 v final squared, which is going to be 1/2 times 30, 10 plus 20, times v final squared was 1.667 squared. And so this is just going to be, your computer right, 42 joules here in this case, right? So the difference between this have more energy than this one. The difference is that this is lost to heat, right, when this collides. So kinetic energy total final is less than kinetic energy total initial, which means that loss to heat, right? Okay, so let's try another one. Let me imagine now that I hang something from a ceiling here, and it's a big mass, it's a 50 kilogram mass, and I'm going to fire which is a 1 kilogram mass, moving at 10 meters per second. All right? Okay. So now this thing can hit it. It's going to basically cause this thing to swing up. And I want to figure out what this height is going to be when it reaches the maximum. Right? Okay, so this is the I state. This is the F state. And so we need a middle state, M, where this is the moment the mass hits it and sticks together. So this moving with some V middle equals question mark. Okay? And then from here it basically moves this. So this is conservation of momentum. And this is conservation of energy. Okay? So let's go ahead and work out some detail here. So M1 V1 initial plus M2 V2 initial, that's just going to be equal to, this was 1 kilogram, this was 10 meters per second, plus this is 50, I believe, times 0. So that's just simply equal to 10. The middle state is M1 plus M2, because they're stuck together, V middle. So that's going to be 51 times V middle is 10. And so roughly speaking, this implies that V middle is equal to 0.2 meters per second, right? So we'll work on this side now, conservation energy. So on the middle state, the total energy is just kinetic energy. It's just 1/2 M1 plus M2 V2 middle squared. Okay? So let's go ahead and work that out then. this is just going to be 1/2 times 51 times 0.2 squared So if you work this all out, this is roughly, I think it's roughly about 1 joule, is that right? Yeah, that's right. This is about 1. Okay. All right. So now the middle part of the mechanical energy, that's 1 joule, sorry. So now the final state, the total energy of the final state is just basically 1/2 m1 plus m2 v2 final squared plus basically the gravitational distance, basically, which is m1 plus m2 g times h, right? So we know that this reaches a maximum height when v2f is 0. So in fact, this term is 0 here, okay? And this will ultimately equal to d2, which is basically 1. So it's going to be equal to 51, so 1 plus 5, 50, times g is 10, times h is unknown, right? And so okay, this is equal to 1. So this will imply h is equal, if you do the math correctly, 0.0002 meters. Okay. Slow swings, but not a huge amount, but the swing nevertheless. Okay. All right. So that's 2 things. All right. So now let's look at elastic collisions. Okay, so in this case, we have 2 conditions. We need to satisfy both conservation momentum and conservation energy. So conservation of momentum. So this looks like m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. Okay, and we have conservation of energy. This is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. This is better be equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Okay, so I have 2 things that we need to do, right? And so you see this is mixed form, this is quadratic, and this is basically linear. So let's try to convert them into something that looks a little better. Right, so to do that, we have to mix match these things. So we move this one here, that one there. So this becomes 1/2 m1 v1 initial squared minus v1 final squared. That's equal to 1/2 m2 v2 final squared minus v2 initial squared. Okay, so just keep in mind that the signs flip, right? Okay, and so this term right here can be written as v1i plus v1f times v1i minus v1f. This thing here can be written as v2f plus v2i times v2f minus v2i. Okay. So now we have something that is very interesting, right? Okay, so let's go stare at this thing very carefully for a second, right? Let me just rewrite this thing as well, let's kill it to 1/2 first. Let's rewrite this thing as V1I plus V1F M1 V1I minus V1F as equal to V2F plus V2I times M2 V2F minus V2I. Okay? Now, this, if I switch this to this side and this to this side, that will get this condition, right? So this one implies conservation of momentum. Implies that M1, in this case, V1I minus V1F is equal to M2 V2F minus V2I. Okay? That just comes from looking at this equation and switching this thing around, which means that this thing here is equal to that thing there, which means that this thing here is equal to that thing. So these can cancel each other out. Okay? So you're left with V1I plus V1F is equal to V2F minus V2I. Let's move everything relative to each other. So this will imply that V1I minus V2I is equal to V2F minus V1F. Okay? So this is a key result here. This one is the relative velocity of approach, and this is the relative velocity of separation. Okay. All right. So you have this condition and this condition, right? I'll call this 1 and 2. So 1 and 2 basically allow you to basically do conservation of momentum with conservation of inelastic collision, right? So let's take a quick example of this, right? Here's my example. Suppose, for instance, I have a mass, which is coming this way. This is basically mass 1. M1 is equal to, let's say, 1 kilogram. V1 is equal to 10 meters per second. It's approaching an object. M2 is equal to 10 kilograms. And V2 is equal to minus 1 meter per second, right? So these things will collide and will bounce off. One will fly this way, the other will fly the other way. And the question is, what is V1F and what is V2F? Right? So that's the question. All right. So let's go ahead and do that. We're going to basically use basic equation 1 and 2. So 1 implies that M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. Okay? And 2 imply that V1I minus V2I is equal to V2F minus V1F, right? So we'll just take a pick of which one we're going to solve and then basically take it from there. So I think of all these four unknowns, I think I'll solve for V1F first, so it means I got to solve for V2F. So that means that this thing right here, let's plug in the numbers here. This one was 10 minus 1 is equal to V2F minus V1F. So this is going to be equal. This implies that V2F is equal to 11 plus V1F. Okay, so that's the first condition. I'll take that and plug it in there, right? So number 1 now becomes, write everything, write it down. This is 1 times 10 plus 10 times minus 1. That's this one. This is equal to 0, which is equal to 1 times V1F plus 10 times V2F. Right? Well, I know that. Plug it in there. So it's equal to V1 V1F plus 10 times 11 plus V1F. So this is just going to be 11 V1F is equal to plus 110, which implies that V1F is equal to, in that case, minus 10 meters per second. Right? And once we have that, V2F is just that. So V2F is equal to 11 plus V1F. So that's basically 11 minus 10 is 1 meter per second. So this flies off at 1 meter per second, and this one flies off at minus 10 meters per second. All right, just basically bounced off each other more or less. Okay. Okay, so that's the answer there, right? Okay, so now that we've done a little bit of 1D collisions, let's look at multi-D collision. So, inelastic collisions in 2D, right? So let's basically make this model here. Consider the following. This is M1 is equal to 5 meters per second. It's going to basically, M1 is equal to 10 kilograms. It moves on velocity at 5 meters per second. This is number 1. Number 2 is moving upward at 4 meters per second. V2 is equal to that. V1 is equal to that. And M2 is equal to 10 kilograms again. Right? So they're going to collide and they're going to stick to each other. So basically you have two masses here, basically, which is M1 plus M2, moving off at some final velocity, which I do not know. Okay? So let's go ahead and solve this. Right? So the thing is that, like, in 2 dimensions, you just do it by component. So just do it. Conservation of momentum in X, Y separately. Okay. All right, so let's do an example here. Okay, so right, so just do so. So let's basically consider the X component and the Y component here. So this is going to be a little bit crazy to subscript, so I'll try to write it nice and big so you can see it. So this is M1 V1 I X plus M2 V2 I X. This is equal to M1 V1 F X plus M2 V2 F X. Right? And similarly for Y, M1 V1 I Y plus M2 V2 I Y. That's equal to M1 V1 Fy plus M2 V2 Fy. Okay. So now we can just stare at this thing. So this first term, this is going to be a 10 this one is going to be a 5, plus this one is going to be a 10 again, but this one has no exponent. In fact, it's 0 on exponent, so that's just 0. So that's 50 is equal to, let's work this one out. Oh, wait, so I forgot. So they're combined together. So that's basically m1 plus m2 VFX, m1 plus m2 VFY. Okay, so let's do that. So it's going to be basically 10 plus 10 times VFX. You can probably guess what this thing is going to look like. This is a 20, a 50, and so VFX is equal to 2.5 meters per second. Okay, now let's do Y. Okay, so now this is just going to be 10. This has no Y component, so that's 0, plus this is 10. This Y component is 4. That's 40 is equal to 20 VFY. So that means VFY is equal to 2 meters per second. Okay, so the final velocity vector is VFX I hat plus VFY j hat. That's just going to be 2.5 I hat plus 2 j hat meters per second. All right. Now, you might ask, what's this angle that it goes off at? Well, that angle is the tangent of theta is equal to VFY over VFX. So that's just going to be 2 over 2.5, which is 0.8, which implies that theta is equal to about 39 degrees. So you can just do your trig and figure out it's actually about 39. Okay. So that's the first example. Let's consider another example. Second is a glancing collision. Glancing collision. So in this case, what we have is that we have an object moving, hits a bigger object. Let's give this thing 1 kilogram mass, a velocity about v1 initial about 5 meters per second. It hits this object, which is 2 kilogram mass. So that's 1, that's 2, right? And it gets separated out. This thing v2 initial is equal to 0. And it gets separated out such that basically this one starts running off in this direction. Number 1, v1f is equal to, I said, 4 meters per second. At some angle, theta 1 equals 30 degrees, right? And then this other one moves off in some direction here, theta 2, right? And this is v2f is equal to some I do not know, right? So you have to do basically both of them separately at some level, right? Okay, so let's go ahead and do this. Let's do the x component and the y component. So in this case, basically, this is just going to be m1 v1ix plus m2 v2ix is equal to, well, this one is going to be 1 times, this is 5, plus 2 times 0. Okay? Now y component is easy. This is m1 v1iy plus m2 v2iy. That both of these are 0, so that's going to be 0 already. Right? And you can do the multiplication. This is 5 essentially. All right. Okay, so given that that is in fact the case, right? Let's look at the final state. So that's the initial state. Final state. Right. So this is going to be, in the x component, this is m1 v1 fx plus m2 v2 fx. This is equal to m1, which is 1 times v2fx is just going to be the cosine of this one, so it's going to be v1f cosine of theta 1, right? Plus, now this is going to be 2 here times v2f. Well, I'll just for v2f, keep it simple like this, right? Okay, so now I'm going to go ahead and solve this thing right now. So v1fx, this was basically 1 times 5 plus this is 2 times 0 is equal to v1f cosine theta 1 plus 2 v2fx, right? So we plug everything out. This was basically 4. Cosine 30 is 0.866, right? Plus 2v2fx, right? And this side is just basically 5, right? So we can go ahead and solve this thing right now. So it turns out this is about 3.46, which implies that v2fx is equal to 0.77. Okay. Now let's do the y component here, right? So in this case, basically I have m1 v1 iy plus m2 v2 iy, right? That's going to be equal to, this is basically 1, that's no y component, that's 0, plus this is no velocity, 2 times 0 is 0, 0, okay? And then let's do the final state here. This one is going to be m1 v1 final y plus m2 v2 final y. So that's going to be 1 times v2 final y, that's going to be v1f sine of theta 1, which somebody will know, plus now m2, that's 2, v2fy, which somebody will want to find out here, okay? So this entire thing is equal to 0, is equal to, right, because these two are equal to each other, is equal to, this is 4 times sine of 30 degrees, that's basically 2, right, plus 2 v2fy, right? So in fact, if you work this out, this implies that v2fy is equal to minus 1, right? Okay. And so, basically then, we're done. v2f vector is equal to, let's see, the first one is 0.77, I hat minus 1 j hat meters per second. Okay, I have a little material on elastic collisions, but I'm going to skip that and basically call it a day.